Steam burns are said to be worse than water burns. Let's find out how much worse. The table below contains some constants that you may or may not find useful. In part A, we're to calculate the amount of heat absorbed by the skin when in contact with 10 grams of water at 100 degrees. In part B, we calculate the amount of heat with the same amount of steam at 100 degrees. And then in part C, we ask what mass of water at 100 degrees C would put in the same amount of heat as the steam did in part B. This is a calorimetry problem. And in all calorimetry problems, we deal with the amount of heat that flows during some change to a system. We have two possible formulas for the amount of heat that will flow. If the system remains in a single phase, i.e. it's always solid, always liquid, or always gas, then we have the formula that Q is equal to the mass times the specific heat lowercase c times the change in temperature delta T. This is sometimes known as the MCAT formula for obvious reasons. Additionally, we have a formula for a heat flow that is valid when a phase changes. In this case, the amount of heat that flows is plus or minus the mass times the appropriate latent heat. Let's examine these two formulas a little bit more carefully to understand how best to apply them. The first formula simply has an equal sign. We know that heat entering a system is a positive Q and heat leaving a system is a negative Q, and this is accomplished in that formula using the fact that delta T takes a sign, either negative for a falling temperature or positive for a rising temperature. So the sign in the first formula within a single phase is automatic. The second formula, on the other hand, deals with an amount of heat necessary to either freeze/melt or boil/condense some amount of material. In that case, depending upon which direction we're going, the heat is either entering or leaving the system. It's up to us to choose between the positive and the negative sign based upon our knowledge of what's really going on. One final comment. We understand that temperature is an average kinetic energy per molecule. Looking at the first formula, we can actually see an historical mistake. The first formula would have been much more sensible if we had multiplied the energy change per molecule by the number of molecules. Instead, we multiplied by the mass. This does increase when the amount of material increases, but it actually hides the physics from us. In the case given here, where we have a lowercase c, this is called the specific heat, and if we had instead used the number of molecules rather than the mass, we would have an uppercase C for the molar specific heat, and one has to keep this in mind when solving any problem. Let's begin with part A. In part A of the problem, we begin with 100 grams of water at 100 degrees C. The water, when it touches the skin, will be brought lower in temperature until the water's temperature matches that of the skin. So in this case, we recognize that we'll be dealing with the MC delta T formula because we aren't changing the phase of the water. So the amount of heat that we're trying to calculate will be equal to the mass of the water times the specific heat of water times the change in temperature. Change in is always final minus initial. And so the final temperature is 37 degrees, the same as your skin, with an initial temperature of 100. Plugging in the known value of 10 grams for the mass of the water and 4186 joules per kilogram Kelvin for the specific heat of water, we find that the heat change of the water is negative 2637 joules. This number represents the heat lost by the water, and assuming nothing went into the surroundings, the heat gained by the hand is the negative of this, which is positive 2637 joules. In part B of the problem, we're to do a very similar calculation, except the initial state begins as steam. In this case, we're going to have to both change the steam from vapor to liquid, and then move that liquid down to the temperature of this hand to complete the process. Since we're dealing with the amount of heat that flows in or out of the water, we're going to have to consider whether heat flows in or out in the process of steam changes to water. Well, clearly for steam changing to water, the heat is flowing out, and so from among our plus and minus choices, we will select minus mass times the latent heat. This formula is not yet complete. We have two kinds of latent heats to deal with: the latent heat of fusion and the latent heat of vaporization. Fusion deals with the boundary between solid and liquid, and kind of even sounds like that. Vaporization deals with the boundary between liquid and gas. Since steam turns to water, we're at the liquid-gas boundary, and so we use the latent heat of vaporization. After the steam has turned from vapor into liquid, it will then continue by coming down to the same temperature as your hand. In this case, we'll be using the MC delta T formula, and we recognize that that formula always automatically takes care of its own sign, so that will simply give us mass of the water, specific heat of water, times a temperature change, which is 37, final temperature, minus the initial temperature of 100. Recognizing that the mass of steam in this part of the problem is the same 10 grams as we had for the water, and that the latent heat of vaporization of water is 2258,000 joules per kilogram Kelvin, we solve to get a final heat flow of negative 25,217 joules. As in the previous part of the problem, this heat represents the heat that left the water and steam. This is equal to the amount of heat that went into your hand, assuming that nothing was lost to the surroundings. Comparing these results, we see that a little bit more than 2,000 joules goes into your hand due to 10 grams of 100-degree water. However, more than 25,000 joules goes into your hand as a result of the same mass of steam, also at 100 degrees C. This is why steam burns are much worse. Finally, in Part C, we're asked to calculate the mass of water required to deliver as much heat as those 10 grams of steam. Since we'll be dealing with water, we'll be staying within a single phase, and so we'll be able to use the MC delta T, or MCAT formula. We'll use the result from the previous part of 25,217 joules as the heat that leaves the water, making it a negative quantity. The mass in this part of the problem is the unknown, and using the 4186 joule per kilogram Kelvin, and a temperature change once again of final minus initial, we're left with only one unknown in the expression, and we quickly solve to find a mass of 0.096 kilograms, roughly 10 times the amount of water in the first problem. And so in round numbers, steam burns are 10 times worse than water burns.